Hey, welcome back to your favorite calculus course. We're going to start with we're going to discuss in this section the fundamental theorem of calculus. We're going to, the central theorem in all of integral calculus. It connects integration and differentiation, enabling us to compute integrals using an antiderivative of the integrand function, rather than just taking those, using the limiting process with those Riemann sums as we previously did. Now, Leibniz and Newton, they exploited this relationship, which started this mathematical development that fueled the scientific revolution for the next 200 years. But we're going to start here initially, before we formally introduce that again and revisit the fundamental theorem calculus. Let's talk about the mean value theorem for integrals. Now, if you remember, the mean value theorem for derivatives was when we had, the slope of the secant was equivalent to, the f of b minus f of a all over b minus a was equal to there is a c in there where it's equal to the slope of the tangent, right? The slope of the secant, there's a c within that a to b such that it's equal to the slope of the tangent. Now, the mean value for theorem revisits that concept we talked about with the average value of a function. We said that if we have this function, it's encompassing all these different y values, that there's, or if you even if you want to think about this just as a block of ice, right? That once this block of ice settles and flattens out, if you will, if it melts, right, then this area for that rectangle, which is the height f of c times your width b minus a, length times width there, is equal to the area. And we know the area under the curve is a to b f of x dx. All right, so the height times the width is equal to that. Well, another way to say that is f of c, the average height, is equal to, if we divide both sides by b minus a, we have the mean value theorem, which is the average value of the function. Okay, so there's your mean value theorem, or in your textbook you'll also see it that way. So mean value theorem, f of c, is 1 over b minus a times the area under the curve there from a to b f of x dx. The average value of a function, average y value over that interval. Just multiple ways of saying that. All right, so let's do one here, the average value of the function. So according to the mean value theorem for integrals, the average value would be 1 over b minus a from a to b of this function f of x dx. 1 over 4 minus 1 from 1 to 4 of 3x squared minus 2x dx. All right, so that's just saying what's the average y value from here to here, right? What's the average y value? Well, it's a third of, now I'm going to go ahead and do the integral. So I've got a third of, we've got x cubed minus x squared from 4 over here. We've got a third. So we plug in the 4 in, plug in the 1 in. What's that? 64 minus 16 minus, and that's 0. And so we got, what's that? A third of 48. So we end up being 16. So it looks like 16, that y value is the average uh, value of that function over that interval. That's just showing you there. All right, so the old fundamental theorem of calculus. So again, we've been introduced to two major branches of calculus. You got your differential calculus, and now we've got our integral calculus. But there's a close connection. If you want to kind of think about some ways they may have thought about the um, anticipated this relationship. So it says there we could look here. Let's look back at our derivative for a minute. You're taking your slope of the secant, which is your change in y over your change in x, right? y2 minus y1 over x2 minus x1, and then we use that limiting process to use that, right, to move that down, right, move that secant line down to the slope of the tangent line. We know the area of a rectangle is height times width, right? That's your area of the rectangle. So you could anticipate, as we did with summation of all those rectangles, if we took the right-hand side on all these, right, anyways, we could approximate the area of the curve with a summation of all those rectangles. Right? And that's how, those could have been thought about. Those were thought about, I should say. Notice also that with differentiation, we've got a ratio, delta y over delta x. And with the integration approach, you've got the product, delta y, delta x, right? An inverse relationship where you've got your division as compared to your multiplication. Again, an inverse relationship between your integral and your derivative, right? So, fundamental theorem of calculus, I know I introduced this last time a little bit early, but formally, again, it states that if we take this antiderivative, if we take the integral, we'll get the antiderivative, and we'll plug in b, and then we'll plug in a, all right? That's your fundamental theorem of calculus, also referred to as, some textbooks will call fundamental theorem of calculus part 2. So, and here, here's a simple example. If you're taking antiderivative of x cubed dx from 1 to 3, you get x to the 4th over 4, plug in the 3, 3 to the 4th over 4, plug in the 1, 1 to the 4th over 4, and you end up with 20 on that. Now, notice here also, it's not necessary to include a constant of integration. Like when we were doing indefinite integrals without a to b, we would get the antiderivative and we would and we'd say plus a constant, right? Because we give the general form of it. Now you don't have to do that for a for a definite integral, because if you notice, if you plug that in, you've got f of b plus c minus, and then you plug in the a, f of a plus c. And then when you distribute that, notice that your c's cancel. So again, with definite integrals, we don't need that plus c. With indefinite integrals, obviously, we need the plus c. All right, so let's evaluate a few of these here. We got x to the 3rd over 3 minus 3x from 1 to 2. So we end up with 8/3 minus 6 minus, now we plug the 1 in, 1/3 minus 3, and we end up with -2/3. Here you can you push the 3 out in front if you want to before you run this integral. So we got 3, and then we've got x to the, now it's to the 1/2, so 1/2 plus 1. We've got 3/2 all over 3/2. In other words, keep change flipped, 2/3 from 1 to 4. And now we're going to throw in the 4 to the 3/2. And then we're going to throw in the 1 to the 3/2. So we got 4 to the 1/2 to the 3rd. In other words, the square root of 4, which is 2. 2 to the 3rd is 8. And then square root of 1 is 1. 1 to the 3rd is 3. I'm sorry, 1 to the 3rd is 1. We got 16/3 minus 2/3, which is 14/3, which is 14 on that. All right, now the integral of the secant squared. So now remember, the derivative of the tangent is secant squared. So the integral of the secant squared here is going to end up giving you the tangent. And you got to do it from 0 to pi/4. So now we got the tangent of pi/4 minus the tangent is 0. Now remember, the tangent's the sine over the cosine. So sine of pi fourths is, sorry about this, I'm running out of room here. Oops. So yeah, sine of pi fourths root 2 over 2, cosine of pi fourths root 2 over 2, sine of 0, 0, cosine of 0, 1. So we just put 1 on that. All right, how about with some u substitution? Evaluate the integral using u substitution. So first of all, if you split this up, that's a common denominator, right? So we got 1/2 dt from pi halves to 0. And then I've got, and I'm going to also change that up so that I put a negative out front. So we go from 0 to pi halves on that. And then plus we've got cosine 2t all over 2. In other words, 1/2 of that from pi halves to 0. Again, that's out of order, so I'm going to put a negative in front, switch that 0 to pi halves. Use that property, and we got 1/2 cosine 2t dt. All right, now notice we do not have cosine of t, it's 2t, so we've got a composite function on this thing. So that's going to be an issue. We're going to have to use u substitution when we do that part. Let's do this one here first. So we've got the negative stays there. We take the integral of 1/2, so the constant stays there. So we got 1/2 t from 0 to pi halves. And then I got plus and negative, so I'm just going to put minus. And now right here, we're going to let u be the 2t. So du dt, so the derivative of u is 2. And then we take the dt to the other side, dt. So if u is 2t, du is 2 dt. So I know the 2t, this part becomes u, so I'll have cosine of u, and then I need a 2 dt. I need a 2 dt. So what I'm going to do is, and I have a 1/2 dt, but I need a 2 dt. All right, so what I'm going to do is I'm going to give it a 4, because I know 4/2 is 2 dt, right? This will be my 2 dt. But if I all of a sudden give it a 4, I got to offset it with a 1/4 there. Okay. But that's my du. See my du? That's the 2 dt right there. So this becomes minus a 4th integral of cosine u du from t being 0 to t being pi halves. Alright, so we got negative. Plug in the pi halves. 1/2 pi halves minus 1/2 times 0 minus a 4th. Now I'm going to take the integral of the cosine, which is the sine. So I got sine of u, sine of u. Now I'd normally put the u, but I'm going to change it back to my t. So u is 2t, because this is in terms of t being 0 to t being pi halves. I'm going to change it back for it. Plug those in. So we got negative pi fourths minus a 4th, and now I'm plugging in pi halves in there. So sine 2 times pi halves, so sine of pi, minus sine of 2 times the 0, so sine of 0, which is 0. And then the sine at pi is 0. Sine at 0 is 0. So 0 minus 0 is 0. 0 times negative 4th, 0. So this just ends up being negative pi fourths. Negative pi fourths minus 0. Right? All right, let's find the area of this region between the x-axis, between this x-axis here, and the graph of x cubed minus x squared minus 2x. Okay. Now, the first thing that we would want to do here is you want to go ahead and find your zeros. You want to make sure, I know we have a visual, but if we didn't, I want to know where these are for sure. It looks like I kind of know, but let's find these zeros because we're trying to find this area as well as this area. Now, if you remember, when we're taking, and we're finding the area, when we're taking the integral, this area in red is going to end up being negative, right, when we're taking the area. Because if you think about that limiting process with those Riemann sums, you've got those y values that are a negative value times your positive width. So these, when you sum all these up, this ends up being a negative area. So what we need to do is we need to take the absolute value of that integral right there. And then it's not going to be an issue with this positive portion, right? This will end up being a positive area. But we're going to have to split that up when we do that to find the total area, right? So number one, let's find our zeros. Let's find our zeros. So we got x cubed minus x squared minus 2x. So we got an x out front, x squared minus x minus 2, x minus 2, x plus 1. So it looks like x being 0, x being 2, x being negative 1. So sure enough, there's the negative 1, there's the 0, there's the 2. We got all our zeros. So we can set this up. So number 2, this area is going to be the integral from negative 1 to 0 of the function plus, now I got to run the absolute value of this one because this is the one in red. So when I go from 0 to 2, remember when I run this integral, it's going to end up being negative. So we got to slap an absolute value on this thing. So 0 to 2 of x cubed minus x squared minus 2x dx. And if I run the absolute value on that, then I have a positive, and I can add those up, right? This positive amount, absolute value of that negative amount, that'll be my total area on that thing. And you can run through, I won't run through this whole thing, but here's the work for it. All right, we get the integral at x fourth over 4, x third over 3, and so on from negative 1 to 0. That ends up being 5/12. And then you run in the absolute value on that one. So let's go back to this 5/12. The other one's negative 8/3. So this part's 5/12. This is negative 8/3. But again, we slap the absolute value on. So it ends up being the total area is the summation of those two, which is 37/12. Okay. So if you're finding the area between the function and the x-axis, find your zeros, integrate, take the absolute values if the function is underneath that x value because the integral part there will be negative. Okay. All right. So earlier we saw the definition of integral over AB was defined using constant b as the upper limit, x as the variable of integration, just like this, right? Now, what if you had the integral of f of t dt, but it was going from a constant a here, right? Constant a to some variable x. Okay, now we've got a different situation in that case. This brings about a discussion surrounding what's called the second fundamental theorem of calculus. So you'll either hear it called the second fundamental theorem of calculus, or some textbooks will call it the fundamental theorem of calculus, part 1. And let's see if we can kind of talk through this second fundamental theorem of calculus with some examples for a second. So it's saying if I take the derivative of an integral from a constant a to a variable x, it just undoes it and gives you the f of x. So for example, let's talk about this for just a minute. If we just leave this in general form. If I'm running the derivative on this, so I'm going to run, I'm taking the derivative, but I'm going to find this integral, right? So I have the antiderivative. So I get the antiderivative plus a constant. This is obviously an indefinite integral. Now let's take the derivative. And if I take the derivative on this, if I take the derivative of the antiderivative, I get the original function. If I take the derivative of this constant, I just get 0. It's just f of x plus 0. In other words, just f of x. So I get back, right? So in other words, they're just undoing each other, right? They're undoing each other. Okay, so we get that. So how about we run that then here? So I get x to the fourth. I'm going to run the derivative, but let me do the integral here. I get x to the fourth over 4. The antiderivative of the cosine is the sine, and I have a plus a constant. Now I run the derivative, 4x to the third, cosine, derivative of constant, 0. So I end up with, well, I started with x cubed cosine x. So you can see how, all right, they undo each other, right? They undo each other. Now what about if we have, let me get my blue. What about if we have a definite integral? So we have a constant on the bottom, we have an x on the top. So we have the derivative. All right, let's run this. We get 3t to the third over 3. Let's cancel obviously from 1 to x. So I'm taking the derivative. Let's plug this in, x to the third minus 1 to the third. The derivative of x to the third is 3x squared. The derivative of the constant here is just 0, so you just end up with 3x squared. So the derivative of an integral, when you're taking the derivative with respect to the variable here of this, in this case, f of t dt, what happens is this x goes in, so they undo each other and that x goes in. As long as you have a constant here, the variable that you're differentiating with respect to is right there, and it goes in. Notice that, 3x squared. So the x is just going in. Okay, that's the second fundamental theorem of calculus. It's just saying if I take a derivative, going from constant to the x goes in, so they undo each other, just leaves you with f of x. Okay, so here's a few examples. Use the fundamental theorem to find dy dx. So A, we're going to take the derivative, oops, the derivative, sorry, 8x t cubed plus 1 dt. So dy dx equals, taking the derivative, x goes in, it just undoes it, so you end up with the x cubed plus 1. That's it on that one. Okay, second one. Now you're going, notice the variable is in the wrong spot. You want the constant down low, the variable up top. So before you even start this, I would rewrite this, put the negative in front, and go from 5 to x, so that now we can apply the second fundamental theorem of calculus, or fundamental theorem of calculus part 1 again, depending on your textbook. Now we take the derivative with respect to x on both sides, so d dx. Now d dx. And you can put that negative out front too, so you got d dx inside. T sine t dt. So dy dx ends up being, now the x goes in anywhere there's a t, because they undo each other, the derivative integral undo each other. You got negative 3, oops, that's an x now, sine of x. So negative 3x sine of x. But again, notice we had to flip-flop where the constant and that variable was to make sure that it fit the fundamental theorem of calculus. All right, now this third one right here, notice I have x squared. Okay, it's not just x there. When you're doing this, okay, now it gets a little bit trickier because you have a composite function. This is the composite function. Let me go to right here. You have to apply the chain rule because we're taking the derivative, we're taking dy dx. which is dy du dx, right? When you're thinking about your derivative here, because you have this substitution. If u is x squared, then you're going to have to, when you're taking the d dx, you've got dy du dx, right? In other words, you've got the derivative of this piece, but then you got to do chain rule on that. So in other words, to sum this up, to make this a lot simpler than it looks here, when you take the derivative, what you want to remember is if you have something besides x up here, right? We have x squared. The chain rule applies because we're taking a derivative here, but we're taking a derivative on a composite function, right? It's not just going from 1 to x, it's a composite function. So they undo each other, but then we take the derivative of x squared. That's all you got to remember. So 2x cosine x squared. And again, that's because we've got this composite function, right? We've got something besides just x up there. So here's another example of that we're going from a constant, not just to x cubed. So it goes in, they undo each other, the derivative on the integral, they undo each other, so it goes in. But then we take the derivative of x cubed, which is 3x squared. So this just ends up being 3x squared e to the negative x cubed, or 3x squared over e to the x cubed. All right, so the net change theorem states that the fundamental theorem of, you know what, I'm going to stop this and do a second part on this.